So, hello everyone. Hope all of you are having a great time, wherever you are. First of all, this is an honor for me to have this opportunity to address such a distinguished audience. So, thanks everyone for coming and bringing your expertise and experience to this conference. For those of you who might be joining us for the first time, this is a student symposium combinatorics for the students who are interested in combinatorics and are using it in their research, supported by Metrics, ASTMS, AMZ, and UNSW. Especially thanks to our sponsorship. Definitely without their help, we couldn't run this conference. This is my great pleasure to introduce my best friend, one of my best friends, Jack Allsop. He's smart guy. I know him since like 5 months ago. That I guess I started my PhD 2 months before him. And he's one of our special plenary because he's a joint winner of Anne Penfold Street Prize, whilst he was an honor student, which I think would be a shame for PhD student like Yuri, Thomas, and me, because led him to win such a good prize. So yeah, he's a smart guy. And he's going to talk about Row-Hamiltonian Latin squares. And yeah, he did his undergrad at Monash and in Bachelor of Science, research with major, extended major in math and minor in computational science. And he continued to do his honor under the supervision of Ian Wanless, which I mean was the same supervisor for me. And yeah, he's talking about Row-Hamiltonian, as I said. And yeah, Jack, just please begin. The floor is yours.
Thanks a lot, Robert. Yeah, so I'll be talking about some work I've done on Row-Hamiltonian Latin squares with Ian Wanless as my supervisor. So I'll start by defining a Latin square. Let n be a positive integer. An n by n Latin square is an n by n matrix of n symbols such that each symbol occurs exactly once in each row and column. So here's an example of a 5 by 5 Latin square whose symbols are the integers 0, 1, 2, 3, 4. And throughout this talk, the symbols of any n by n Latin square will be the integers 0, 1 up to n minus 1. And we'll also index the rows and columns of a Latin square by 0, 1 up to n minus 1. And indexing the rows and columns in this way means we can think of an n by n Latin square as a set of n squared triples of the form RCS, where R indicates the row of the Latin square, C indicates the column, and S indicates the symbol in row R and column C of the square. And thinking of Latin squares in this way has some benefits. It highlights the symmetry between the rows, columns, and symbols of a Latin square. And that symmetry is important. It leads us to this definition. So let L be a Latin square. A conjugate of L is a Latin square obtained from L by uniformly permuting the elements of each triple. So there's 6 permutations on 3 elements. So each Latin square has 6 conjugates. And we label each conjugate by a one-line permutation, which gives the order of the coordinates of the conjugate relative to the order of the coordinates of the original square. So, for example, the 1, 2, 3 conjugate of a Latin square is just itself. And the 2, 1, 3 conjugate, where we swap the rows and columns, that's just the matrix transpose of the square. Let L be a Latin square and let I be less than J. We can consider row I and row J of L to be a permutation in 2-line form, which we call the permutation mapping row I to row J, and we denote this by Rij. And we call the set of all such permutations the set of row permutations. And when we represent a row permutation in cycle notation, we call each cycle in a row permutation a row cycle. And we can define column cycles and symbol column permutations and symbol permutations similarly to this, and taking conjugates of a Latin square interchange the row, column, and symbol permutations. So for example, on the left here, we have row 0 and row 1 of the Latin square from the previous slide. So if we consider this as a two-line permutation, that's the row permutation R01 of this square, which in cycle notation is the 5 cycle 0, 2, 1, 3, 4. And now we can define what a Row-Hamiltonian Latin square is. So an n by n Latin square is called Row-Hamiltonian if all of its row permutations are n cycles. And we can construct a simple family of Row-Hamiltonian Latin squares using group theory. If you take the Cayley table of a group and you remove the borders, then you're going to get a Latin square. And this theorem says that the Cayley table of a group forms a Row-Hamiltonian Latin square if and only if the group is cyclic of prime order. So they give us a simple family of Row-Hamiltonian Latin squares. And for a Latin square L, we let nu of L denote the number of conjugates of L, which are Row-Hamiltonian. And if we're talking about a family of Latin squares, and every Latin square in the family has the same value of nu, say nu equals c, then we'll also say that that family of Latin squares has nu equals c. And each Latin square has 6 conjugates, so nu is an integer between 0 and 6. And Wanless showed that a Latin square is Row-Hamiltonian if and only if its 1, 3, 2 conjugate is Row-Hamiltonian. And so that implies in particular that nu of L has to be even for every Latin square. And Latin squares whose conjugates are all Row-Hamiltonian are of particular interest, and they're called atomic. And so, for example, we saw that the Cayley tables of cyclic groups of prime order were a family of Row-Hamiltonian Latin squares, but in fact, they're actually atomic. So it's a simple family of atomic Latin squares. And so it's known that n by n Row-Hamiltonian Latin squares can only exist when n is 2 or n is odd. And it's conjectured that Row-Hamiltonian Latin squares exist for all odd orders. But we're way off proving that. There were only 7 previously known infinite families of Row-Hamiltonian Latin squares. And any Latin square in these families has order either p, p squared, or 2p minus 1 for an odd prime p. And all of these families either have nu equal 2, nu equal 6, or a mixture of Latin squares with nu equal 2 or nu equal 6, but none of them with nu equal 4. And so we have constructed an infinite family of Latin squares with nu equal 4. But before going through that, I'm going to talk about something in graph theory called perfect one factorizations, which are related to Row-Hamiltonian Latin squares. And I'll demonstrate what a perfect one factorization is on the complete bipartite graph K55. So a perfect matching or a one factor in a graph is a subset of the edges such that every vertex is incident to exactly one edge. So the orange edges here form a one factor in K55, as do the blue edges, purple, red, and green edges. And now every edge has been colored. So we've partitioned the edge set of K55 into one factors. And this is an example of what we call a one factorization. And if we go back to just the blue and orange edges, you can see that these edges form a Hamiltonian cycle in the graph. And that's actually true if you take the edges of any 2 different colors, those edges are going to form a Hamiltonian cycle in K55. And so that is an example of what we call a perfect one factorization. So in general, a one factorization of a graph is a partition of its edge set into one factors. And then we call that one factorization perfect if the union of edges in any 2 distinct one factors forms a Hamiltonian cycle. So another example, here we've got a one factorization of K8. So the complete graph on 8 vertices. So on the top line, you've got the 7 one factors which create this one factorization. And you can see that the edges in the second and third one factors form a Hamiltonian cycle in K8, but the edges in the fourth and fifth one factors don't. So this is an example of a one factorization of K8, which isn't perfect. What does this have to do with Latin squares? Well, this theorem says that there exists an n by n Row-Hamiltonian Latin square if and only if there exists a perfect one factorization of Knn. And the proof of this theorem is constructive. So given a Row-Hamiltonian Latin square, you can construct a perfect one factorization of a complete bipartite graph and vice versa. And I'll go through how to do this, and I'll demonstrate the construction with this 5x5 Row-Hamiltonian square on the left. So to go from a Latin square to a one factorization, you label each vertex in the top part of K and N by vertices by labels C0, C1 up to Cn, Cn minus 1, where the vertex Ci corresponds to the ith column of the Latin square. And then you label the vertices in the bottom part by S0, S1 up to Sn minus 1, where each label corresponds to a symbol of the Latin square. And then for every row of the Latin square, we can define a one factor in the graph. And we do this by adding an edge from Ci to Sj whenever symbol j is in the ith column. So in this example, we consider row 0 of this Latin square. And in column 0, you have symbol 1. So we add an edge from C0 to S1. And in column 1, we have symbol 2. So we add an edge from C1 to S2. Column 2, we have symbol 4. So we add an edge from C2 to S4. We add an edge from C3 to S0 and C4 to S3. And we've gone through the row, and now we have a one factor. And in general, whenever you do this process, you're always going to obtain a one factor from each row because every row of a Latin square is a permutation of the symbol set. And then we go through and we do this for every row until we've got a set of n one factors. And this is always going to give us a one factorization, this procedure, because no two edges from distinct one factors are ever going to overlap. And that's because every column of a Latin square is a permutation of the symbol set. So yeah, following this procedure, you're going to go from a Latin square to a one factorization of a complete bipartite graph. And you can actually just do the exact reverse of this construction to go from a one factorization of a complete bipartite graph to a Latin square. And then this one factorization that we get in this way, that's going to be perfect if and only if your Latin square was Row-Hamiltonian. And so the reason for this is, suppose that we've gone through this procedure and we have a one factorization of K and N. Then consider the graph whose edges are the union of edges in the one factors coming from row I and row J of the Latin square. Then every vertex in this graph has degree 2, so it's going to be the union of cycles. And so we can write each cycle here, like what we've done on the slide. You can write each cycle as Ci1, Si1, Ci2, Si2, up to Cik, Sik, back to Ci1. And then it's not too hard to show that the corresponding row permutation in the Latin square Rij is going to contain the cycle I1, I2, up to Ik. And so it's clear that this row permutation is going to be a full cycle permutation if and only if the graph whose edges come from those two one factors is a Hamiltonian cycle. And so the Latin square is going to be Row-Hamiltonian if and only if this one factorization is perfect. So just to finish off this example, we have here the graph whose edges the edges coming from the one factors from row 0 and row 3. And we can write, this is a Hamiltonian cycle, and we can write it as we've done on the slide here. And so from that previous result, it says that the row permutation R03 of this Latin square should be the 5 cycle 03241. And we can check that. We just take row 0, row 3, treat that as a 2-line permutation, and we do get the 5 cycle 03241, which is what we want. So that's how you go from an n by n Row-Hamiltonian Latin square to a perfect one factorization of k and n. And yeah, as I mentioned, you just do the exact reverse of this to go from a perfect one factorization of k and n to an n by n Row-Hamiltonian Latin square. All right, so why do people care about perfect one factorizations of complete bipartite graphs? There's a couple of reasons. So one reason is that they can be used to construct what we call n infinity Latin squares. And these are Latin squares which contain no proper Latin subsquares. And lots of work has been done on constructing these sorts of Latin squares, but the problem of existence of these squares is still open. There are still some orders for which we don't know whether or not there exists a Latin square which contains no proper Latin subsquares. Another reason is that it's been suggested that perfect one factorizations of complete bipartite graphs can be used to store data on an array of hard drives in such a way that allows for easier recovery after failures. And I don't believe that this application has ever been implemented, so it might not be totally honest to call this an application, but people have written papers on saying theoretically you can use perfect one factorizations of complete bipartite graphs for this reason. So there is maybe some applied reasons why people would want to study these as well. And another reason to care is because of its relationship to Kotzig's conjecture. So in 1964, Kotzig conjectured that there exists a perfect one factorization of the complete graph, K2n, for all positive integers n. And this is a fairly well-known conjecture. And this is related to perfect one factorizations of complete bipartite graphs by this theorem, which is also due to Kotzig, which says that if there exists a perfect one factorization of k n plus 1, then there exists a perfect one factorization of k and n as well. And in fact, sometimes you can construct multiple different perfect one factorizations of k and n from a single perfect one factorization of k n plus 1. And Kotzig's conjecture is a long way off being resolved. So there are only 3 known infinite families of perfect one factorizations of complete graphs. And these families cover complete graphs Kn, where n is p plus 1 or 2p for an odd prime p. And along with these 3 infinite families, we have some sporadic results on when perfect one factorizations of complete graphs exist. So here we have n on the left is just the number of vertices in the complete graph, and on the right we have the person who, or the people who discovered the perfect one factorizations of that graph K. And so, yeah, we have a bunch of sporadic cases, and the smallest n such that it's not known whether or not there is a perfect one factorization of Kn is n equals 64. And we also have some results on the number of different one factorizations and perfect one factorizations of complete graphs. So here, yeah, this table on the left, we've got the number of one factorizations of Kn for some small n, and on the right, we have the number of perfect one factorizations of Kn. And on the table below, we have who counted these numbers. And note that we've only got even values of n here because for a graph to have a one factor, let alone a one factorization, we need to have an even number of vertices. And what this table shows us is that one factorizations of Kn are relatively common, but perfect one factorizations are very rare. Now we've got the same, this is the same table, but it just shows the one factorizations of the complete bipartite graph and the perfect one factorizations of the complete bipartite graph, and again, who counted them. And this table, it tells us the same thing. It says that one factorizations of K and N are relatively common, but perfect one factorizations are not common at all. So yeah, finding perfect one factorizations of these graphs, it's a hard problem. And I'll end the discussion of perfect one factorizations with some justification of why there are very few Latin squares, known Latin squares with nu equal 4. So we've seen that given a perfect one factorization of kn plus 1, you can construct a perfect one factorization of knn, sometimes multiple, and then you can construct an n by n Row-Hamiltonian Latin square. And out of the 7 known infinite families of Row-Hamiltonian Latin squares, 6 of them come from the families of perfect one factorizations of complete graphs in this way. And Wanless and Ehrig showed that any Row-Hamiltonian Latin square constructed from a perfect one factorization of a complete graph in this way must have nu equal 2 or nu equal 6. So that mostly accounts for why the known Row-Hamiltonian Latin squares have nu equal 2 or nu equal 6. All right, so now that I've hopefully motivated the study of Row-Hamiltonian Latin squares, and in particular Latin squares which have nu equal 4, I'll work towards defining the Latin squares which we studied, which we showed has nu equal 4. So I'll need to go through some definitions. Let L be a Latin square. A square which can be obtained from L by permutation of the rows, columns, and symbols is called isotopic to L. And this isotopy operation, it preserves the lengths of row cycles. And if we apply the same permutation to the rows, columns, and symbols, we obtain a Latin square, which we call isomorphic to L. And if we apply the same permutation to the rows, columns, and symbols of L, and we get L back, then we say that that permutation is an automorphism of L. All right, so here is another Latin square, and this Latin square has some nice structure. This is an example of what we call a diagonally cyclic Latin square. So an n by n diagonally cyclic Latin square is a Latin square which has a cyclic automorphism of order n. And so as a result, that means that the sequence of symbols on any broken diagonal, which is just a diagonal which wraps around the square when it reaches a border, the sequence of symbols on any broken diagonal form a sequence of consecutive integers modulo the size of that square. So here, the highlighted cells are a broken diagonal of this square, and you can see that the symbols on this broken diagonal form a sequence of consecutive integers modulo 11. And so, more generally, you can define a diagonally cyclic matrix of order n, whose symbols are the integers 0, 1, 2 up to n minus 1. Which is just a matrix which has this property that the symbols on any broken diagonal form a sequence of consecutive integers modulo n. And it's clear that any such matrix is uniquely determined by its first row. So a natural question to ask is what first rows of a diagonally cyclic matrix are going to give you a Latin square. So to answer this, I'll need this definition. Let G be a group written additively and phi a permutation of G. Then we call phi an orthomorphism if the map which sends x to 5x minus x is also a permutation of G. And now we can answer the problem. So let L be a diagonally cyclic matrix of order n with first row defined by L naught J is 5J. Then L is a diagonally cyclic Latin square if and only if phi is an orthomorphism of Zn. So if we want to investigate diagonally cyclic Latin squares, we need to look at orthomorphisms. And I'm going to look at a particular type of orthomorphism called cyclotomic orthomorphism. So let P be a prime and let nk equal P minus 1 for some positive integers n and k. And let gamma be a primitive element of Zp star, which is Zp star is just the set of units in Zp, so it's Zp minus 0 under multiplication, and that's cyclic of order P minus 1. And then for J in 0, 1 up to n minus 1, we define a cyclotomic coset Cj by the formula on the slide. So for example, C naught, that's just the set of all nth powers of gamma. And that is, that's the unique subgroup in Zp star of index n. And then taking n elements A0, A1 up to A n minus 1 in Zp, you can define a cyclotomic map by mapping 0 to 0 and by mapping x to ai multiplied by x, where x is in the ith cyclotomic coset. And a cyclotomic map, which is also an orthomorphism, is called a cyclotomic orthomorphism. So let's RP and NP denote the set of squares and non-squares in ZP. Also, it's called the set of quadratic residues and quadratic non-residues. So the simplest type of cyclotomic map is a cyclotomic map of index 2, which is called a quadratic map. And these have some benefits to study. Firstly, they're defined for all odd primes. And also, in general, a cyclotomic map depends on your choice of primitive element gamma. But when you're dealing with quadratic maps, the choice of gamma doesn't matter, because the cyclotomic cosets C0 and C1 will always just be RP and NP, respectively. And we also have some pretty simple necessary and sufficient conditions for a quadratic map to be an orthomorphism. So yeah, a necessary and sufficient condition for the quadratic map phi AB to be an orthomorphism is that AB and A-1 times B-1 are both squares. And such a map is called a quadratic orthomorphism. So if we combine this result with the result which says that a diagonally cyclic matrix whose first row is an orthomorphism is a Latin square, then we can define this infinite family of Latin squares. So let A, B, and ZP, let A, B, B, and ZP, which satisfy the conditions from the previous slide, then this map phi AB is an orthomorphism, and we can define the diagonally cyclic Latin square whose first row is defined by phi. And we're going to denote that Latin square by LAB. So explicitly, LAB is given by the formula here on the slide. And it's difficult to find Row-Hamiltonian Latin squares, and that's demonstrated by the lack of known infinite families. And this is because the condition of being Row-Hamiltonian is very strong. But these Latin squares, whose first rows, these Latin squares LAB, these give us some hope of finding Row-Hamiltonian Latin squares because of this lemma. So let P be a prime and let AB be elements of ZP such that the Latin square LAB is well defined. If P is 1 mod 4, then to show that LAB is Row-Hamiltonian, you only have to check the row permutations R01 and R0C for some quadratic non-residue C. And if P is 3 mod 4, you only need to check the row permutation R01. So instead of checking every row permutation, you only have to check 1 or 2, depending on P mod 4. And the reason that this lemma is true is because these Latin squares have a huge automorphism group. Because they're diagonally cyclic, they have the cyclic automorphism of order n, but also the map which scales everything by a quadratic residue is also an automorphism. And also the map, I'll say this because we'll need this later, the map which scales everything by a quadratic non-residue, that's an isomorphism between the Latin squares LAB and LBA. And there is a natural generalization of these Latin squares to Latin squares of prime power order. I won't go through that, but this basically you can construct these Latin squares of prime power order, and this lemma still holds. And in this paper from 2005, Wanless, he had lots of success in finding examples of Row-Hamiltonian and atomic Latin squares of this form, because this lemma reduces the workload that you need to show that a Latin square is Row-Hamiltonian. And many of the examples, the sporadic examples of perfect one factorizations of complete graphs and complete bipartite graphs come from this paper and come from Latin squares of this type. And we considered a particular infinite family of Latin squares of this form. So let P be a prime, which is 1 or 3 mod 8, and denote the P by P Latin square L minus 1, 2 by LP. And P being 1 or 3 mod 8, these are just the conditions so that this is a well-defined Latin square. Then explicitly LP is given by the formula on the slides. And Wanless conjectured that these Latin squares have nu equal 4. except for the Latin squares L3 and L19, which are known to be atomic. And we proved this conjecture. And I'll briefly go through how we did this. So the first step to show that these Latin squares have nu equal 4 is to show that they are Row-Hamiltonian, except for when P is 3 or 19. And so we know that we only have to check either one or two of these row permutations, depending on P mod 8. I'll go through how we did this for the 3 mod 8 case, and the 1 mod 8 case is very similar. So we know we only have to check the row permutation R01 of LP. And then to show that this was a P cycle, we use a result of Beck, which is some linear algebra. So let Sn denote the group of permutations on the set 0, 1 up to n minus 1. And let sigma 1, sigma 2 up to sigma k be transpositions in Sn. And let tau be the n cycle 0, 1, 2 up to n minus 1. And then we define sigma to be this product of those permutations. Then we can define a symmetric k by k matrix, A sigma over Z2, by this formula on the slide. And we call this the link relation matrix for the permutation sigma. And then Beck showed that this permutation is an n cycle if and only if this matrix is non-singular over Z2. And I should mention that Beck's theorem is actually a bit more general than this. This is just more of a special case of Beck's theorem. And so with our Latin squares, let phi be this quadratic orthomorphism phi -1, 2. Then using the formula for LP, you can show that the row permutation of LP is just this Latin squared defined in equation 1. It's this permutation defined in equation 1. And that can be written quite nicely in cycle notation, which is equation 2 here. And so using this, it's not too hard to come up with a formula for the link relation matrix for the row permutation R01 of LP. And we'll denote that matrix by AP. So it's the P minus 1 by P minus 1 matrix defined here on the slide. So this is the matrix A11. And this matrix has some nice structure. So if you look at rows 3 and 4, and note that 3 and 4 are quadratic residues, modulo 11, then these rows agree on all columns except for column 9. And this is true in general. Whenever you have consecutive quadratic residues, their rows in the matrix AP are going to agree on all columns except for 1. And if you look at rows 7 and 8, and 7 and 8 are quadratic non-residues modulo 11, then these rows agree on all columns except for columns 7 and 8. And again, that's true in general. Whenever you have consecutive quadratic non-residues, their rows in the matrix AP are going to agree on all columns but 2. And we use this structure to prove that this matrix was non-singular over Z2. So we showed that when you have one of these two situations here, where consecutive rows differ on either 1 or 2 columns, you can choose 2 rows to delete and delete the same 2 columns to obtain another symmetric matrix over Z2 of order 2 less than previous. And you can do this in such a way that the determinant mod 2 is preserved. And then we showed that you can continually do this until you reach a 2 by 2 matrix, which has determinant 1. And we did this in 3 different stages, and I'll highlight each stage on this matrix A11. And when I refer to the ith row of the matrix, I'll be talking about the row which was originally the ith row before any deletions occurred. But the rows and columns will be labelled to make that clear. So the first stage, we take all consecutive quadratic non-residues, I plus 1, and then we delete both rows I plus 1 and columns I plus 1. And whenever we do this, we're going to preserve the determinant modulo 2. So in the P equals 11 case, the first such pair is 6 and 7. So we delete the highlighted rows and columns to get this matrix. And now we don't have any consecutive quadratic non-residues left. So we're up to the second stage. And in the second stage, we go through each remaining quadratic non-residue, so K. And then there's always going to be a pair of consecutive rows perhaps the rows weren't previously consecutive, but they're now consecutive after doing some deletions. There's going to be a pair of consecutive rows which agree on all columns except for column K. And then we can delete one of those rows and row K and the same set of columns, and the determinant mod 2 is going to be preserved. So we go through the quadratic non-residues left. First we have 2. And if we look at rows 4 and 5, these agree on all columns but column 2. So we can take row 2, row 4, delete those, delete the same columns to get this matrix. Now we go to the next quadratic non-residue, which is 8. And if you look at rows 1 and 3, these rows agree on all columns except for column 8. So we can delete row 3, row 8, column 3, column 8, and we're down to a 4 by 4. And now the only remaining quadratic non-residue is -1. And then we stop there. We don't delete -1. I should have mentioned that earlier. And so now we're up to the last stage. And in the last stage, we just showed that the first 2 remaining rows always disagree on exactly one column, say column I, and then we can delete the second remaining row and column I, and row I, and the same set of columns. And that's going to preserve the determinant modulo 2. So here, row 1 and row 5 agree on all columns except for column 9. So we delete row 5, row 9, and the same set of columns. And now we're down to a 2 by 2 matrix, and this has determinant 1 mod 2. So because we preserved the determinant mod 2 in this process, that means that the matrix AP is going to have determinant 1 mod 2, and so it's non-singular over Z2. And so by Beck's theorem, we know that the row permutation of LP is a p-cycle, and so by that previous lemma, we know that LP is Row-Hamiltonian. And the 1 mod 8 case, we use very similar ideas. All right, and so once we've shown that LP is Row-Hamiltonian, we knew that nu of LP was either 2, 4, or 6. And so the next step to showing that nu was 4 is to show that these squares aren't atomic, unless P is 3 or 19. And to do this, we showed that the 3-2-1 conjugate of LP is not Row-Hamiltonian. So this Latin square here is the 3-2-1 conjugate of L11. And the highlighted cells here show us that the row permutation R01 of this square contain the 3-cycle 875. So the 3-2-1 conjugate of L11 is not Row-Hamiltonian, so L11 is not atomic. And we showed that this is true always. We showed that every row permutation of the 3-2-1 conjugate of LP contains a 3-cycle, except when P is 19. And so that says that the 3-2-1 conjugate of LP is not Row-Hamiltonian unless P is 19 or P is 3. And so the Latin squares are not atomic in this case. And so we know that nu of LP is either 2 or 4. So we've shown, so remember that a Latin square is Row-Hamiltonian if and only if its 1-3-2 conjugate is. And so we've shown that LP, and hence its 1-3-2 conjugate, are Row-Hamiltonian. And we've shown that its 3-1-2 conjugate is not Row-Hamiltonian, and so neither is its we've shown that the 3-2-1 conjugate is not Row-Hamiltonian, so neither is its 3-1-2 conjugate. So nu of LP is 4 if and only if the 2-1-3 conjugate of LP is Row-Hamiltonian. And so in this paper, Wanless wrote, where he studied these squares, he showed that every conjugate of a Latin square, LAB, is a Latin square of the same type. And you can get all the conjugates of a Latin square using these rules. So the 1-3-2 conjugate of LAB is L A inverse B inverse if A is a quadratic residue, and it's LB inverse A inverse if A is a non-residue. And the 2-1-3 conjugate is L 1 minus A 1 minus B if P is 1 mod 4, and it's L of 1 minus B 1 minus A if P is 3 mod 4. And using these two, you can get all 6 conjugates. So we're interested in the 2-1-3 conjugate of LP. And this says that depending on whether you're 1 or 3 mod 8, the 2-1-3 conjugate of LP is either LP itself or it's L2 minus 1. which we said earlier is isomorphic to L minus 1, 2, which is just LP. And because isomorphism preserves the length of row cycles, we know that the 213 conjugate of LP is always Row-Hamiltonian, and hence nu of LP is 4, which was our goal. And now I'll just go through an algebraic application of our results. So we were able to use our Latin squares to solve a problem on quasi-group varieties stated by Falconer. But before I go through before I can state that problem, I'll have to go through a bunch of definitions. So let Q be a set with a binary operation. Then we call this pair a quasi-group if for all A, B in Q, there exists unique X, Y in Q such that equations 1 and 2 on the slide are satisfied. And then we call Q a loop if there exists some element of Q which acts like an identity. And finite quasi-groups are an algebraic equivalent to Latin squares in the sense that the multiplication table of every finite quasi-group is a Latin square, and every Latin square is the multiplication table of some finite quasi-group. So we call quasi-groups Q and P isotopic if the multiplication table of Q can be obtained from that of P by a permutation of the rows and columns, as well as a permutation of the elements of P. And in this case, we call P an isotope of Q and vice versa. And you can notice that if Q and P are finite quasi-groups, then this definition is equivalent to saying that Q and P are isotopic if their multiplication tables are isotopic as Latin squares. And if Q and P are loops, then we call them isotopic if they're isotopic as quasi-groups. And in this case, we call P a loop isotope of Q and vice versa. And we know that every quasi-group is isotopic to at least one loop. So let E be a set of quasi-group identities. The quasi-group variety defined by E is the set of quasi-groups satisfying all identities in E. And the loop variety defined by E is the set of loops satisfying all identities in E. So for example, the quasi-group variety defined by the associative identity is just the set of all groups. I'll go through some particular types of varieties. So we call a variety anti-associative if the only group it contains is the trivial group. And we call a loop variety isotopically L-closed if it's closed undertaking loop isotopes. And now we can state Falconer's problem. So Falconer asked if there exists a non-trivial anti-associative isotopically L-closed loop variety. And we used our Latin squares to solve this problem. So let Q be a quasi-group and let X be an element of Q. Then the map Lx, which is called the left translate by X, that's the map which is defined by multiplication by X on the left. And similarly, the right translate by X is just multiplication by X on the right. And so let P be a prime, which is 1 or 3 mod 8, but not equal to 3 or 19. And then consider these two identities here. Now, if Q is a finite quasi-group, then Q satisfying this first identity, that's equivalent. So this map Ly composed with Lx inverse, that's equivalent to the row permutation Rxy of its multiplication table. And the map Ry composed with Rx inverse, that's equivalent to the column permutation Cxy. So if a loop Q satisfies the first identity, that's equivalent to saying that every element of every loop isotope of Q has left order dividing P. And because of what we just mentioned, in the case where Q is a finite quasi-group, that's equivalent to saying that its multiplication table is Row-Hamiltonian. Now, if a loop satisfies the second identity, then that's equivalent to saying that every element of every loop isotope has right order coprime to P, which in the case where Q is finite, it's equivalent to saying that no column cycle of Q is a P cycle. And we showed that the loop variety defined by these two identities is a non-trivial anti-associative isotopically L-closed variety. So Because these identities concern the left and right orders of every element of every loop isotope of a loop, it's not too hard to see that this is going to be isotopically L-closed. And also the left and right orders of elements in a group are the same. So if a group satisfies the first identity, then that tells us that the order of every non-trivial element is P. But then if it satisfies the second identity, that says that the order of every non-trivial element is co-prime to P. So the only way a group can satisfy this is if it has no non-trivial elements. So the group must be trivial and the variety is anti-associative. And so it just remains to show that this variety is non-trivial, and that's where our Latin squares come in. So the Latin square LP is Row-Hamiltonian, and no row permutation of the 3-2-1 conjugate of LP is a P cycle. And taking conjugates of Latin squares interchanges the row, columns, and symbol permutations. So if in particular we take the 2-3-1 conjugate of LP, the row permutations of that Latin square are just the row permutations of LP, and the column permutations of that square are just the row permutations of the 3-2-1 conjugate. So that Latin square is a Row-Hamiltonian Latin square, and none of its column cycles are a P cycle. And because, so we know that every quasi-group is isotopic to a loop, so there is some loop whose multiplication table is isotopic to that Latin square, and hence that loop satisfies these two identities, and it's in the variety. So the variety is non-trivial, and that's how we showed that there exists a non-trivial, anti-associative, isotopically L-closed loop variety. And for each of these primes, you get a different variety. So we showed the existence of infinitely many of these. All right, so just to summarize, we constructed the first infinite family of Latin squares with nu = 4, proving a conjecture of Wanless, and this allowed us to construct infinitely many non-trivial, anti-associative, isotopically L-closed loop varieties, solving the problem of Falconer. And this gives us some ideas for future research. So to solve Falconer's problem, we needed to construct a Latin square such that every row cycle had length P and no column cycle had length P. So we'd like to explore the following problem. If you're given co-prime integers A and B, can you construct a Latin square L such that every row cycle of L has length A and every column cycle has length B? And then another direction for future research comes from these Latin squares LAB. So we use the result of Beck to show that our squares were Row-Hamiltonian. And so we'd like to use Beck's theorem to find other families of Row-Hamiltonian Latin squares of the form LAB. Here's a plot which shows the number of Row-Hamiltonian Latin squares of this type versus P. And you can see that the number of squares seems to grow linearly with P. You get slightly different growth in the case where you're 1 mod 4 and 3 mod 4, but that's to be expected because we saw that the lemma, which characterizes when these Latin squares are Row-Hamiltonian, in the 3 mod 4 case, you only need to check 1 row permutation, whereas in the 1 mod 4 case, you have to check 2. But either way, the growth seems to be linear. And so ideally, we'd like to show, using Beck's theorem, that the number of these Row-Hamiltonian Latin squares grows linearly with P. Unfortunately, there doesn't seem to be any real pattern in the pairs AB, such that LAB is Row-Hamiltonian. And also, other than the pair -1, 2, there doesn't seem to be any constant pairs which always work. And yeah, that's my talk. So thank you.
Thank you a lot, Jack. Feel free to react to Jack's talk, reaction on the bottom. That was such a terrific talk. No wonder you won the prize with this talk. So is there any questions from the audience? That's give them some time to write their questions. Here's a question from Angus. For the conjecture on the last slide, are there any assumptions, asymptotics known for those who for those two families?
I'm not sure. I'm not sure about the question. Sorry.
For that conjecture on the last slide,
Yeah.
are there any asymptotics known for those two families?
Oh, no, I don't think there's much known at all. Yeah, no, I don't think there's anything known at all, really.
Thank you. No. Can I ask a question? But I'm not sure which page it was. Before you define the loop, I guess the slide before defining the loop, you were talking about some results in are you sorry?
Before define the loop, so this one?
Yeah, this one. Is there any relation between, because I know that the number of, is a concept that there's a relation between this conjugate, 6 conjugate, and the number of transversal induction squares. Do you have anything in mind about, because you were talking about proving that determinant is somehow odd in mod 2. So is there a relation between that we can say, for example, there's a matrix or for Latin squares, we have at least one transversal because the determinant is 1? Or
I don't know. I haven't put any thought into how this relates to the transversals, to be honest. Yeah, no, it's a good question, but I'm not sure of the answer there. I have to think about that.
Thank you. So if there's no any other questions, let's thank Jack again.